For the next 20 or so minutes, I'd like to just introduce some of the main features of BurnMan. And I guess the difference to all of the other talks is that I won't be talking all that much about geodynamics. And part of that is because BurnMan is a Python code. It runs significantly more slowly than fully compiled languages. And you will see from several of the other speakers later on today how we can start to integrate thermodynamics in a more real-time, on-the-fly sense. What I really want to talk about is how we can use tools like BurnMan to really prototype and start thinking about a lot of the ideas behind geodynamics without understanding in a deep sense all of the thermodynamics behind it. Essentially, all of the thermodynamics is packaged up for you. And so you can just play around with things yourself and try to understand the basic physics of how things work. So the installation, first of all, of BurnMan is quite simple. Pip install. There's now, I think, our manual is something like 500 pages long, but the beginning is written in a way that should be clear to everyone. If you want to know how a bit of the software works, then you can find a section that's tailored specifically to your problems. So the original vision of BurnMan, as it was envisaged in the 2012 CIDER project, was really to investigate the magnesium-silicon ratio of the lower mantle. And that was born of a few papers that were published in the years before the CIDER workshop that had suggested that the lower mantle was significantly more silica-rich than the upper mantle. And so the idea was to implement something in Python that would allow us to investigate all of the equations of state and really try to work out whether the VP, VS, and densities of the lower mantle fit the idea that it was particularly silica-rich. You may or may not have kept up to date with the literature since then, but people haven't got, I think, or at least the community as a whole hasn't got any closer to answering that question. And so it's always worth revisiting that, and other people may be talking about that later today. Since BurnMan was written initially, it's now grown to be a general purpose toolkit for petrologists, for seismologists, for geodynamicists, and for planetary scientists. And so we published a paper in JOS 3 years ago, the Journal of Scientific Software, that basically introduced all of the things that I'll be talking about today. The general structure of BurnMan as a Python toolkit is essentially a series of different Python classes that all fit together to be able to build up in a modular way how we understand the physics of thermodynamic and geodynamic systems. So we start from the very simplest level with a bunch of mineralogical Endmembers. So, for example, we've got forsterite here and fayalite here, and those go into two different classes now in BurnMan. The mineral class, which gives you all of the thermodynamic properties, at least the scalar thermodynamic properties, and also a Caliban class, which is built essentially for people working at synchrotrons and for people looking at petrology, which gives you a lighter version of the mineral class that just gives you density characteristics as a function of pressure and temperature, or pressure as a function of volume and temperature. Those different Endmembers are then collected together into various solutions, and those can be solid solutions or melt solutions. So for the two Endmembers of olivine, those go into an olivine solution. There are similar for orthopyroxene and garnet for whatever solid solutions you can think of. And then those different solid solutions can get packaged together and put inside another class, which is our composite class, which essentially forms the basis for all assemblages that we might think of. So, for example, a Hartsbergite rock. Composites can then be packaged into larger composites. So you can have multiple different rocks with different fractions of those rocks. You might imagine that you could have a slab made of a certain fraction of basalt and a certain fraction of Hartsbergite and mix those together as well. From a seismic or a density perspective. Coupled with those composite classes is an averaging scheme. So just knowing the phase proportions and the compositions of all of our different phases and also the pressure and temperature of the composite itself is not enough to be able to tell us what the effective isotropic velocity, seismic velocities of that composite are going to be. And so we can also tack on another class called an averaging scheme class, which can take a bunch of different models that help us to approximate, at least in a 1D sense, the texture of that rock. So the Voigt band, the Royce band, the Hashim-Strickland bounds. And then in addition to the material classes, so mineral, calibrant, solution, composite, we also have a bunch of other classes that go along with BurnMan to help us achieve whatever modeling goals we have. So either to understand the layer of a planet or an entire planet, or the seismic velocity structure as a function of depth. And one of those is the geotherm class. And so there are a bunch of different geotherms packaged within BurnMan, which you can then interrogate either as a function of pressure or as a function of depth. So to give you an idea of how we build up these different classes, starting off with the Endmember class, we essentially just give the class a dictionary full of the different parameters, and that includes the equation of state. I'll talk about the equations of state in the next slide, but we have lots of different ones for you to pick from. And then there are a bunch of different parameters. So like, for example, the Helmholtz energy, the volume, the bulk modulus, all standard temperature and pressure. These different parameters will change depending on the equation of state that you choose for your material. This is the initialization down here. So Forster-IT equals BurnMan.mineral, and then you give it the params. And then after that, you can call that material for basically any one of the thermodynamic properties you might need. So you can, for example, ask Python to give you an array of different pressures and another array of different temperatures. You can make a grid of those. So this is now a 2D grid of pressures and temperatures. And you can pass those to this mineral and ask it to evaluate the various different properties. So for example, the Gibbs, the volume, and the thermal expansivity, and it will give you those in exactly the same format as you've given it the pressures and temperatures. You can now also do this for solid solutions and give an extra set of arrays at the end here for different compositions. So in one line, you can calculate everything that you want to your, basically to your heart's content. I should say that throughout the rest of this presentation, all of the things in orange, these are all tutorials or contributed files or examples that will help you to be able to do the things that I'm describing during this talk. One of the really nice things about BurnMan is that it allows you to prototype and test things. So if you are designing something new, like a new equation of state, or you're thinking, oh, maybe I shouldn't use the Birch-Moynihan equation of state, maybe I should use something else, then you can very quickly swap various different equations of state in and out using the same parameters for each, and work out what happens, what works. What the differences in properties should look like if I use different equations of state. And so there's an example here from a paper that I published last year where I introduced a new equation of state. This is for shock experiments and in expansion as well as in compression. And essentially what I wanted to do in this figure is show you that some equations of state are good in certain circumstances and some are bad. So we have quite a lot of common equations of state that are all programmed up into BurnMan. There's the Vinay equation of state here, Birch-Moynihan 3, Birch-Moynihan 4. So Birch-Moynihan 3 is used in, for example, the Stixrud and Lithgow-Bertoloni databases. The modified Tate is shown here in green. That's used in the Holland and Powell databases. And then there are various other ones used for other purposes. And you can see where those equations of state fail or don't as you go to extremes of volumes. And you can do that basically in just a few lines of Python code. Another thing that is implemented in BurnMan is that you can add on various different components. So if the basic Gruneisen-Debye equation of state that you're using seems to fail for some reason, then you can add on other components that you think might be there. So for example, magnetic components or anharmonicity you can include. And so I've given an example on the right-hand side of this figure of the effect of using the add-on for anharmonicity. You can see that at high temperatures, it's actually way above the melting point of fayolite, but nevertheless, you might want to interrogate an equation of state outside its stability field. You can see that without anharmonicity, you get this decline of the bulk modulus until it reaches zero, and then your equation of state fails. But if you include an anharmonic term, nothing fails and everything behaves quite nicely again. And so this is a nice way to play around with various different bits of equations of state. And of course, you can do the same thing with solutions. And the nice thing about BurnMan is that solutions are defined in a very human readable format. So you don't have to go into some text file somewhere and translate all of the complicated expressions for entropy, for example. You can just, sorry, look at how the solution is declared. There is one parameter which is just called the name, which is just the name. You can choose whatever you like. And then the solution model argument, there are a bunch of different classes for different types of solutions. So this is the asymmetric regular solution, which is used by Holland and Powell. And then there are a bunch of independent Endmembers, and these are drawn from databases that are already written for you. So this is the Holland and Powell dataset 6.2, the pyrope, the armandine, the grossular, and andradite components. And then the mixing terms are written in a very nice human readable form. So basically the square brackets here dictate which different species sit on each one of the different sites. And the number after those square brackets gives you an indication of the multiplicity of each one of those sites. And then within that single expression, that gives you the ideal entropy of mixing for those solutions. Then for each one of the solution models, there are different terms. So for example, the asymmetric parameters, the Van Laar parameters, which are just called alphas here, and then energy interaction terms. So this, for example, is the energy of interaction, the first term here, between pyrope and armandine, and so on and so forth. And that, again, allows you to prototype various different things. And so there's a paper that I published basically explaining the mathematics of solid solutions, which I published with Jamie Connolly in 2021, where we essentially do a bunch of very simple prototyping and show you the origins of convergent ordering and non-convergent ordering in solid solutions as they are used by the geological community. And so again, here, this is also provided as a contribution package within BurnMan. There are a bunch of different databases. So within BurnMan, there's already packaged databases from Lars and Carolina from 2005 all the way up to 2024. There's the Decoker and Stixrud databases for liquid silicates and oxides. There's Saxena and Ericsson if you particularly fancy looking at sulfides, which are particularly difficult phases to model. And then the Holland, Powell, Green et al. Databases from at least 2011 to 2025. And there are many others, and most of these are added either by me or other people who have used BurnMan over the last few years or so. One of the nice things about BurnMan is that because it's written in this modular way and because it doesn't take all that many lines of code to make a figure, all of the data sets are tested and benchmarked quite thoroughly to the original figures. And so here is one of the figures from Stixrud and Bertoloni, 2024. And one of the things that I've been doing recently is working with the developers of other codes to provide secondary benchmarks so that we can make sure that all of our codes within the community provide the same results, at least within a few joules per mole. All of the tests that are here are maintained within the code base. They're run and checked before any modifications are allowed to the main software branch on GitHub or the release on PyPy. So, of course, no code is perfect. We always find bugs. Every piece of thermodynamic software in the community contains bugs. One of the things that we try to do is make sure that when we find bugs, we introduce a new test to make sure that we can't get the same bug in the future, and to make sure that we won't end up seeing the same bug again in another way. Some other things that have been added recently to BurnMan is relaxation processes. So many different phases, both solid solutions and pure phases, exhibit anomalous properties that arise from state-driven changes in things like electronic spin state from high to low spin iron, for example, in magnetic ordering, in species ordering. So magnesium ion exchange is a very common one, but coupling between aluminium and magnesium silicon is another one. Also structural flexibility. So for example, the rotation of particular units within minerals, tetrahedral units or octahedral units. All of these things can cause phases to exhibit anomalous properties that equations of state, as written in the community, cannot handle very well. And so what BurnMan uses is essentially Landau theory to be able to model these in a simple and extensible way. And this allows us to look at second derivatives of the thermodynamic potential, so heat capacity, thermal expansivity, compressibility as a function of pressure and temperature. One of the nice things about BurnMan is that we can turn off or turn on all of those anomalies. So this is particularly interesting when we have things like species ordering that may happen quickly on the timescales of geodynamics, but happen slowly on the timescales of seismic wave propagation. And so we can actually look at those relaxation processes of order, disorder, and make predictions about what we should see in terms of velocities and geodynamic behavior. And so one of the examples that I wanted to show that I have published over the last couple of years is that we've made a modification to equations of state so that now we can look at full anisotropic properties of basically everything. So we can look at the cell tensor, the unit cell tensor. We can look at seismic velocities as a function of orientation. We can look at the thermal expansivity tensor, essentially any of those thermodynamic, thermoelastic properties that you may be interested in. We can now create an equation of state that allows users to just select the pressure and temperature and composition, and it will give you the full anisotropic properties. So here's an example on the left-hand side for San Carlos olivine, and you can see in the upper left, we're changing in pressure and temperature, and as a result, the P wave velocity and the S wave velocities are changing. And of course, you can interrogate that at any particular temperature and pressure. One of the other nice things about developing this is that we can also look at other things like, for example, the relaxation that I was talking about before. For example, looking at the spin transition or other various transitions. And so here on the right-hand side again is an example that I published last year, looking at displacive transformation in SiO2. So this is between Stishovite and post-Stishovite. And if, again, we have a look at this on the right, this Q parameter essentially looks at the tilting of the SiO6 octahedra within the stishovite. A Q parameter of 0 indicates that there's no tilting. A Q parameter of more than 0 indicates that it's tilted in one direction, and -1 and a negative Q indicates that it's tilting in the opposite direction. For anyone who's taken an undergraduate level course in thermodynamics, hopefully you remember that the Gibbs energy is minimized at a given pressure and temperature for any given phase assemblage. And so what we can do is we can look at the shape of that Gibbs energy curve as a function of pressure and temperature, and we can look at what the most stable phase should be. So if I show the simulation, you can see that we have this convex down shape that decreases as you increase in the pressure. And at some point, you get to the point at which we don't have a single minima, we have two minima. And that's the point at which we can have that spontaneous octahedral tilting, which is this displacive phase transformation. At the bottom, you can see that our model also allows us to predict the A, B, and C parameters of stishovite. And so again, this is an output of our equation of state, which is within BurnMan. One of the other nice things is that we can calculate all of the various elastic moduli, and we can therefore make an estimate about what the reduction in velocity should look like as we go through the transition. We can do exactly the same thing for composites. So as we're building up assemblages, we can join whichever end members and solutions that we want and build them into a composite object. These can all be interrogated at different pressures and temperatures to obtain all of the model material properties that we want. So here's an example on the right-hand side showing, first of all, the instantiation of two different solution objects, so bridgmanite and ferropericlase. We then set the composition of those two objects, and then we create an assemblage out of those. And from that, you can use the evaluate method, as you did before, to work out what the densities and the velocities are. So that's Vp and Vs. As I mentioned before, we can tack on various different material averaging schemes to allow the user to calculate multiphase seismic velocities under different assumptions: Voigt bound, Royce bound, Hessian-Strickman upper and lower bounds. And those can have a really big effect on, for example, the shear modulus, as is shown on the right-hand side of this slide. And last of all, we can build all of our assemblages, all of our composite materials into planets and into layers, essentially to be able to prototype what we should expect various different planets to look like under different assumptions. So here again, on the right-hand side, I've shown you a little bit of BurnMan code with, for example, all of the properties that we need to be able to build a planet. So the lithosphere, asthenosphere boundary radius and the temperature, the convecting mantle radii, so this is just an array, a NumPy array. And then we create a BurnMan layer object, which contains the radii and a name for the layer. We can give material to that layer, so in this case, a pyrolite object, and apply a boundary layer perturbation. So this essentially approximates what we should see geodynamically. So we have thermal boundary layers at the top and the bottom. Those boundary layers have increased thermal gradients, and therefore the density changes more at those boundary layers. And we can put all of these things together, and we can very quickly prototype a planet so that it fits, for example, PREM. And so this is one of the exercises that I give to my third-year students. I essentially give them a bunch of different composite material objects and ask them to build up a planet that matches the mass and the moment of inertia of Earth. I also give them the opportunity to play around and say, okay, how much can you change things and still get these gross observational features? So in the last couple of minutes, I'd like to just briefly introduce a couple of tools. So BurnMan will allow you to fit various properties of Endmembers and solutions to observational data. So I use this whenever I do high pressure experiments, or whether I'm reviewing someone's paper where they've done high pressure experiments, just so that I can check that their equations of state are robust, or my equations of state are robust. And so you can take any data that you like, whether that be volumetric data or heat capacity data or thermal expansivity data, put them all into a package and ask BurnMan to give you the best fitting equation of state with propagation of errors all the way through those calculations. We can identify bad data using extreme value theory. We return the full covariance matrix along with chi-squared and other statistics to hopefully give people confidence that what they found is of high quality. We can also use BurnMan to fit compositions. So here, these are essentially, so what I've done here is I've taken a bunch of experiments that were provided by Berker and Fay in a paper in 1997. They provided all of the phase compositions and also the bulk composition of their sample, but they didn't provide estimates of phase fractions. So essentially how much of each phase was in their rock at each pressure and temperature that they did their experiments at. So we can throw all of these into BurnMan and estimate what the phase fractions are, and therefore be able to compare those with, for example, the output predicted by the Holland and Powell databases or the Stiksrud and Lithgow-Bertoloni databases. We can also run simple equilibration schemes. So for anyone who is familiar with the thermocalc thermodynamic software, this is essentially a clone of what thermocalc does. So you take bulk composition, you take an assemblage where you actually know what the different phases are, you take a couple of equality constraints along with free compositional vectors, and you press equilibrate, and it will calculate for you the equilibrium phase assemblage. You will see in later presentations today that there are various different softwares that will allow you to basically take out the equality constraints and do this in an automated sense for any pressure, temperature, and bulk composition that you like. We have made the decision not to do this within BurnMan because at the moment it is a pure Python code and it would be way too slow within pure Python. There are many other tools that you can use, including MageMin and Hephaestus, which will do these things much more quickly. Another thing that is essentially a clone out of thermocalc is that in 1994, Roger and Tim demonstrated that you could use probe measurements of samples to provide a unique optimal estimate of pressure and temperature conditions of the formation of a given rock assemblage. So a metamorphic rock that you can have in your hand and you can sample with electron probe, given a certain thermodynamic data set and uncertainties. And so this is now implemented within BurnMan, and you can use it on any data set. So here's an example on the right-hand side where I've done this for the Stiksrud and Lithgow-Bertoloni data set in 2024 for magnesium ion partitioning between olivine and Wadsleyite. And the use for this can both be for experimentalists to, for example, reduce the uncertainties on pressure and temperature estimates in the lab, or of course it can still be used for metamorphic petrologists to take real rocks and estimate what the pressure temperature conditions of formation should have been. A last thing that I'd like to add is that one of the postdocs working with me has been writing a C++ version of BurnMan, essentially to be used as a backend, and the speed up is on the order of a factor of 1,000. So hopefully we'll be able to do more complicated things in the near future. And last of all, because this is a geodynamics webinar, is that I'd like to say that there are many, many things that will be done in the next few years that are really exciting, and you'll be hearing about some of these later on today. So most simulations today essentially look at changes from a thermodynamic viewpoint, look at changes with respect to temperature and volume, or changes with respect to temperature and pressure. For the most part, we haven't been putting in the thermodynamics of changes in composition, but this has been pioneered in the last few years by Boris Kaus's group and others. We haven't looked all that much at metastability, although there have been a few papers from the early 2000s, for example, looking at metastable preservation of olivine within subducting slabs, for example. I think this will become much more common in the next few years. And finally, we've not really done very much in the way of stress chemical coupling. And I think this will become much more important as we start to consider situations where we have mushers in magma chambers behaving as real mushers. So actually starting to consider individual crystals within a mush and stress chains working within that mush, which can significantly change how the material behaves rheologically. So this stress chemical coupling is really important for dictating what the viscosity of a substance is. And I think we will be starting to see many more papers in this field over the next few years. Okay, thank you very much for listening.